Okay, welcome back. We just started talking about setting up reservations for system traffic. In this previous example, we were showing you how to set a reservation for management traffic, granting 500 megabits guaranteed for management traffic as management traffic hits any network adapter. Now, this, of course, is not going to be the case where you just have one network adapter and then you have a distributed switch. You're going to have probably a larger environment. Hopefully, on every host, you'll have at least two adapters, and you'll have multiple hosts. So say, for instance, here we have two hosts. Each host has two adapters, right? So that means we really have, if you count all the adapters, 10 gigabit per adapter, 40 gigabits of total aggregate bandwidth. So when it comes to counting up our actual resource allocation settings, when you have something like a type of reservation that entails some kind of traffic that will be distributed across all the adapters, you actually aggregate all the reservations across all the adapters. Now that most likely is going to only be applicable to VM traffic. So for instance, you'll notice here in this scenario, what if we had defined system traffic reservations for every single physical NIC, right? I know the picture shows just that NIC over on the right hand side, but these settings apply to each and every NIC network adapter on our two hosts here. So each host's network adapter has half of a gig or 500 megabits reserved for management traffic. We've got 1 gig reserved for iSCSI traffic. We have 1 gig reserved for fault tolerance traffic, 1 gig for vMotion traffic, 500 megs for VM traffic. So we basically have reserved altogether 4 gigabits of network bandwidth, leaving 6 gigabits available as unreserved. It's not necessarily free capacity, but they just haven't been reserved. So now we've reserved just 40% of our total 10 gigs of bandwidth, noting that that is well under the maximum that we could reserve of 75% of that 10 gigs of bandwidth. All right, so now let's take a look here. We've got two hosts, two adapters per host. That's 40 gigabit total here. How much, or I should say, how many network adapters would management traffic ever use at any one time? Well, on one host, the management traffic will actually only use one adapter. That's just how the management traffic is going to work. Same goes with iSCSI. It'll use just one adapter, unless you set up port binding, for instance, on 2 VM kernel ports. But each VM kernel port will get one adapter. So that's be 1 gigabit for iSCSI traffic per adapter. vMotion also uses one adapter. Fault tolerance uses one adapter. But VMs are a bit different, right? Because you might have maybe a couple dozen virtual machines. Well, what's going to happen is the distributed switch, no matter where the VMs are placed, the VMs are actually going to have their traffic distributed across the different uplinks on each host. So in that case, that 500 megabit of reserved bandwidth per adapter really does aggregate across all the adapters. So with the 4 adapters, that's a total of 2 gigabit for VM traffic, reserved out of the 40 gigabit of total bandwidth. We can see all that, in fact, once you've set these up in the vSphere client. So for instance, here we've got all those same settings down below. We've got our management traffic reserved to 500 megs. We've got our fault tolerant to 1 gig. vMotion is 1 gig. VMs are 500 megs and 1 gig for iSCSI traffic. And then everything else here, we're not setting reservations for. Now, having all these set up across our top part of this interface will then show, okay, we have, well, actually, what's important over here, it even says you've got, how many adapters and what the minimum speed you've got. It's 10 gigs. So that's important. When you build any kind of distributed switch, you want every host to have the exact same network capacity, right? You don't want to have one host that's got 1 gig bandwidth and then all the other hosts are 10 gigs, because these calculations are all going to be based on the worst case scenario, the 1 gig adapter you've got on your environment. So you want everything to be at the same speed. So if they're all 10 gigs, this makes this very simple, because now we're looking at our system traffic reservations and we have 10 gigs to work with per adapter. The most we could reserve is 7.5 gigs or 75%. And we have currently reserved up to this part, right? We basically have reserved up to 4 gigs and we have 6 gigs of unreserved bandwidth. Again, I know the user interface is available. So, I mean, that's what we could reserve, right? Because remember, when you reserve, you're sitting on a minimum guarantee. In fact, it's just like any other reservation. This resource must be available in order for a VM to power on and to actually utilize that resource. But what's important to note here, you may be wondering why the VM reservation seems unusually small. That again is 500 megabits per adapter, but because VM traffic is by design going to be distributed across all the uplinks, across all the hosts in a cluster on a distributed switch, those 500 megabits really do aggregate across every single adapter on every single host. So say for instance, what if we had 5 hosts, right? If we have 5 hosts and then each host has 2 adapters, so that's 10 total adapters, a 500 megabit system reservation for VM traffic is actually going to aggregate to a total of 5 gigs of system bandwidth reserved for VMs. So remember, now we actually have 10 adapters that are 10 gigs each. So we have 100 gigs of bandwidth. 5 of those 100 gigs are guaranteed to the VMs. Now again, don't forget, this is not a limit. This is not what they're only able to use. This is what they're guaranteed to use. So you want to be careful with these reservations. You don't want to set them too aggressively anyway. You're just making sure that there's a minimum amount of bandwidth for VMs to be able to utilize. And then after that, they compete with whatever bandwidth there is. Remember, by default, VMs already get double priority over all the other type of traffic that's on that distributed switch. But what's neat is that this, now the 5 gigs of VM traffic reserved as system traffic, this basically becomes your top level pool in this resource hierarchical resource management capability that is being defined. You can now create more network resource pools that draw their reservation from the top reservation defined here as our system traffic. So now we can create, say for instance, a network resource pool called Pool A. We'll have a 2 gig reserved from the 5 gigs, and we'll have Pool B have a network reservation of 3 gigs pulling from the parent of 5 gigs. So now both of these resource pools are essentially using their parent pool's reservation to draw from, just like how we can do this with resource pools for things like CPU and for memory. Once you have the network resource pools, the next thing to do is then assign the port groups, or I should say to assign the resource pools to the port groups. So here we have a tenant A port group. We can assign that port group to the network resource pool A. So now that port group basically has 2 gigs reserved for it. And we have the tenant B port group who's assigned the network resource pool B, so this port group has 3 gigs. Now the VMs in their port groups are then able to then basically utilize their teams, or I should say their their network port groups total amount of reserve bandwidth. So we have the tenant A port group can, as a group, the VMs can reserve up to 2 gigs. And over here in the tenant B port group, those VMs as a group can reserve up to 3 gigs. But that's not how much each VM is going to get, right? That's just what the VMs get as a group. So let's see what the VMs are going to be able to get individually in the next part. So we'll take another quick break here, and we'll come back and we'll take a look at how we assign this at the virtual machine level. So stay tuned. We'll see you in the next section.